This is the second part of a worked example on vertical circular motion, a more complicated example which I've had to split up into two videos. If you were not expecting it to be a second part, if you thought it was just a worked example on its own, you might want to just go back and check the first half, make sure you've seen the first half. So it's a continuation really. If you recall, we were looking at a situation where we had a particle being launched at the bottom on a string, launched at the bottom of its circular path, the string hitting a peg, and the particle carrying on in a smaller circular path around as it goes around that peg there. And in the first part, we were asked to calculate the minimum speed to give it at the bottom in order for the smaller circle to be completed. And we took an energy approach to look at change in speeds in the large part of the circle, and then we used a combined approach, energy and forces, to look at the journey on the second circle, second smaller circle. And in particular we were interested in the forces because we wanted to establish something at which the tension had to be greater than or equal to 0 at the top of the circle there. So we have come out, we went through a couple of energy stages, and then we looked at the forces here. We did it in a general case, not just going straight up to the 90 degrees, the top of that circle there. And we're about in part B, we're about to pay the benefit of why we've done that. We could have just actually in this first part, we could have just gone straight up to substituting 90 degrees in straight up here somewhere further up in the answer. But in a moment in part B we'll see why it was a good idea to get this general angle case. We had got as far as establishing that u squared, in order for it to make a complete small circle, u squared had to be greater than or equal to 9g over 2. So now we can just calculate the minimum u straight away from that. So minimum u must be square root of 9g over 2, and if you type that into your calculator you get something which rounds to 6.6 meters per second. If we're going for 2 sig figs, I think it's 6.64 or something like that. But at 2 sig figs, which we should be using because we've used 9.8 for g, 6.6 is absolutely fine. It's worth having this exact version, as they call it, the exact version of it here as well. I suspect we might need to use that in the second part of the question, which is, and if we'd used 6.6 we'd be getting all kinds of inaccuracies coming in, so it's worth having that rather more algebraic exact version of u there as well. So let's have a quick look at part B. So let's just whiz back up to the question and see what part B was about. So given that P is projected with 90% of this speed, the speed that we've established in part A, calculate the angle between PQ and the vertical when the string becomes slack. So we're looking at this smaller circle now. We've given it less speed than it needs at the bottom of the big circle. So on this journey up, the smaller circle here in the very top section there, at some point it's not going to have enough speed, it's going to run out of speed and it's going to fall back inside the circle here, and that will happen when the tension becomes equal to 0. The thing that we're trying to work out is what angle that tension, that bit of string, the radius there, will make when that tension becomes 0. And that's why it was a good idea in the first part, as I was just saying, to have this general expression for t in terms of theta. Because now we've saved ourselves lots of work in the second half, or lots of repetition anyway, in this part here, because we've already established that thing about the relationship between the tension and the angle. So we know that now we're starting with 90% of our minimum speed, so now we want to say that our new u for this part of the question is going to be 9/10 of root 9g over 2. And the other thing that we're interested in is that the string is going to go slack, so the slack implies that the tension equals 0, and we had an expression for our tension, So we can just set that expression equal to 0 and substitute this u into it, and hopefully that will leave us with something in which g is the in which theta is the only unknown. So I'm just looking, I'm taking this part here, the right hand side of that t expression. Here is the expression that t is equal to, so therefore I can use that expression and just set it equal to 0 because of this condition that we've got down here. So that I write down somewhere else that I don't have to flip between the screens, went 2m brackets u squared minus 3g minus g sine theta in a bracket there, and that was then minus mg sine theta. That was our right hand side expression for t, so that's what I'm using in place of the t here, so that must now be equal to 0. So that's nice. We notice that there's an m in the two terms there which can cancel out. I could expand here and tidy up a little bit as well, because I've got a g sine theta term coming up twice, so let's just tidy that up a little bit here. So now we're going to have 2u squared minus 6g, and then we're going to have a minus 2g sine theta and another minus g sine theta, so minus 3g sine theta must be now equal to 0, so that's good. Let's just rearrange that one more step and get u squared out from it. So u squared is going to be equal to 3g plus 3g over 2, 3g sine theta over 2, or 3 over 2g sine theta, or however you want to think about that one. Let's have 3g over 2 there and times sine theta. That's quite handy because we've got a u value to substitute in here now, so we can substitute u into this u squared on the left hand side, and that should make everything rather nice and dandy. So squaring all of that stuff, 9/10 squares up to 81 over 100, and then we've got the expression in the square root. So just getting rid of that square root gives me a 9g over, on the bottom, was it 2? Yeah, 9g over 2. So 81 over 100 times 9g over 2 instead of my u squared must be equal to 3g plus 3g over 2 sine theta. And so that's nice. We've now got ourselves an equation in which every term has a g, so the g's cancel out, and everything else is just numbers apart from theta. So we should be able now to solve this one. So we've got 3 over 2 sine theta. 81 times 9, what's that? 729, isn't it? 720, oops, that looks like a 2. 729 over 200. Doesn't look much like a 7 still, does it? Sorry about that. Minus 3. Got everything right there? Yeah, that looks okay. So 729 over 200, take away 3, that's 129 over 200, isn't it? So let's go for 3 over 2 sine theta equals 129 over 200. Yeah, I can fairly easily get that down to sine theta, so I can cancel out a 2 and make that 100 on the bottom, can't I? And I can cancel out a 3 and make that 43 on the top. Sine theta is equal to 43 over 100, and theta must be the inverse sine of 0.43. And if you type that into your calculator, what you get there is 25.467 ... Just checking back to the question. I notice, I think I remember, yes, we want the angle between PQ and the vertical, and what I've calculated is the angle between PQ and the horizontal. So I'm going to need to subtract the answer I've got for theta from 90 degrees. So I can just finish this one off by saying, therefore, angle with vertical is 64.5, blah, blah, blah. And as usual, we should give, actually G cancel out here. I could give this to 3 significant figures if I wanted, but it's an angle, 0.5. Let's go with 3 significant figures here. 64.5 degrees. So there we are. I hope you can recognize that as a much more complicated example. Remember that it's combined with the previous video that made one question, a much more complicated question than the previous worked example that I posted a video up of. But I wanted you to see a bit of a range. The issue here really is that there's lots of variety that we can get into these questions. It's fairly difficult to predict precisely what kind of angle they're going to take on things. It's the broad principles that you need to be very comfortable with. And the broad principles really are just conservation of energy, changes in kinetic energy being balanced by changes in gravitational potential energy, being aware that you need to be very careful calculating changes in height. That's where it often goes wrong. So there's that one technique for addressing things, and usually what you get out of it is something to do with the speed. And then the other technique to be applied to it is this idea about radial acceleration, and so the component forces in the radial direction being equal to mass times radial acceleration. So that's a case of resolving forces and doing an F equals ma, with A being usually V squared over R, but also sometimes R omega squared, but much more commonly mv squared over R for our ma. So I hope those 2 worked examples over the 3 videos give you a bit more insight into the kind of approach for vertical circular motion. I'm perfectly happy to do more of them. This is a difficult topic. I can do lots and lots of examples of these if they're useful, and if you're keen, if you don't feel you're on top of the subject yet and you're keen to get on top of it, you can just let me know if you want any more.